Welcome to physics class, and today I'll be telling you the topic in a jiffy. We have discovered from Bohr's atomic model that electrons revolve around the nucleus in circular orbit, sometimes called energy levels. And that energy level of an electron are limited to individual values called quantized values. The energy of such electron is then said to be quantized. This leads us to a topic called energy quantization. Like I said earlier, if you have really seen that video on atomic models, where I try to explain the fact that Bohr's atomic model came up with the fact that the energy of the revolving electrons around the nucleus must be fixed. You know, that fixing means it doesn't change. For example, the energy of the electron at this K shell must be the same. It does not change. So the energy becomes the same, and that is why it has to revolve around this orbit. So there is no intermediate energy level. That means if I have another energy level or another orbital, and the electron at this place can never be said to have left this orbit. It's just like people racing in a track, and they must all maintain that track. So that is what we mean by quantization. Now, that model of or theory of quantization of atom has led to different inventions, and that is why it's very necessary for us to delve into this topic called energy quantization. Now, by the end of this lesson, you should be able to explain the idea of energy quantization, explain energy levels in an atom, define ground state, define excited state, explain emission of light energy on return to the ground, or what we call atomic spectra. Sit back, relax while I take you through these topics. The meaning of energy quantization. The whole idea of energy quantization is that radiated energy is not continuous, but can only exist in discrete or fixed values called quanta. Now, let's continue this aspect of the theory which I have on the board. The word quantized means exist only in discrete values. So Bohr was saying that there is no intermediate energy levels. That means that the energy at this two level and that of this point must be fixed. So the electron can never leave this place and come to this place to be. It is not possible. So that they are quantized, they are fixed, and they keep going. However, there could be a transition from one energy level to the other. So that is what we mean by fixed or discrete level. And each of these shells is called, it can be 1, 2, 3, or KLN, and all the rest of them. So that is what quantization is. So the energy at this level is unique to that level. The energy at this two is also different and is unique to that too. But whenever there is a transition from one energy level to another energy level, there is something that happens. There must be an emission of a radiation, and that is what has given birth to electromagnetic radiations, which we are going to be learning, like the radio wave, gamma ray, and all the rest of them. Now, energy levels in an atom are also known as electron orbit or shell. They are paths through which electrons revolve around the nucleus of an atom. Energy levels are usually represented by horizontal line. Okay, you know, this one, and this one. So these can also be seen as energy level, which is this place is infinity, and then this level. So we can use horizontal line also to represent this energy level. Just like we can also use this kind of configuration where this is the nucleus with positive charge, or proton and neutron inside. We can also represent them in this one according to Bohr's model. Now, the ground state. The ground state of an atomic nucleus or molecule is the lowest energy level. Now, look at this. These are excited states. This is the ground state. Now, electron in the ground state can absorb energy to transition to excited state. So, let's assume these are different horizontal lines to represent these energy levels. Now, in absorption, electron will go up to the excited state. So when you absorb energy absorption, what happens? You now go from one ground state to a new ground state. What I'm saying is that a ground state can be this particular place. So what happens when radiation hits it? What happens? It now transitions to a new energy level, maybe to this next one, or it can even go to another level. Maybe let's say KLM. So when this radiation hits this particular electron or particle, it now transitions, it now jumps to the next level. So that is what we mean by energy absorption. And energy released, and then when it is at this level, it's at the excited state, at the up state, it can release energy, give off energy, and then return to the ground state. So that is from one level to the other is called energy absorbed and energy released. When an electron is released from the ground state to any of the higher energy levels, it is said to be excited state. Excitation occurs when an atom is heated or bombarded with an energetic particle such as photon. Now, the energy required to raise an electron from the ground state to its excited state is called excitation energy. Like I have said before, so there is not much to talk about here. Just like an electron in this level, let's say at this particular level, when it is bombarded by a kind of energy or radiation, it now jumps from one energy level to another energy level. So we say that what happens at that point is called excitation. And how do you excite an atom? It is by heating it or by bombarding it with an energetic particle. So this is incoming of photon. It is coming from up, down, and this is the ground state, which is the lowest level, and this is the upper place, is called the excited energy level. Now, equation for photon. Now, the equation for photon emission is given as this. This is change in E, which is change in energy level, En, E naught. So E sub n is telling you the excited state, the upper state, and this one is the ground state. And according to Planck's constant, because that the energy given off is directly proportional to the frequency. The energy given out by this electron and by this particle is directly proportional to this frequency, and this frequency is equal to hf. All right? So this is called change of the energy from one energy level to another. For example, if this place is 2 and this is 1, then from this level to this level, which is called change in E, which is E2 minus E1, and which is equal to hf. And remember that light can be given as C is equal to F lambda. Therefore, F is equal to C over lambda. Sometimes we can say that this is change in E is equal to E2 minus E1 is equal to hc over lambda. So these are different ways, and this lambda is the energy of the excited state. So it can be E2, all right, given up on the process of transition. Now, looking at this is energy of the emitted radiation. This is the energy in the excited state, and E naught, energy in the ground state. H Planck, which is 6.6 times 10 raised to power minus 34 joules seconds, is the Planck's constant. This is the frequency of the particle, and c is the speed of light. Now, this equation, we said equation for photon emission, we said an electron excited to an energy level E2 of this force to the ground state, this, calculate the frequency and wavelength of the emitted photon. Let's start with this calculation. So from E2 to E naught, remember that we said that change in energy is En minus E naught is equal to Hf. This is equation 1. We can also say that this E naught minus E sub 0 is equal to H C over lambda. Now we are going to do our substitution. So E2 is minus and E naught is minus 2,1, you know. So I'm going to do my substitution. They say I should calculate the frequency. So what I'm going to first find is my energy change, which is given as minus 2.42 times 10 raised to power minus 19, then minus, so simply put plus 21.8 times 10 raised to power minus 19. So this minus this. So in this case, what I'm going to do is to factorize. Remember, 10 raised to power 19 is here and 10 raised to power 19 is here. I'm going to put it 10 raised to power. I'm going to have 10 raised to power minus 19 in bracket. This is 21.8 minus 2.42. And this is going to be, this is going to be 1.938 times 10 raised to power minus 18 joules. So this is the energy. This is the energy given off when electron from a excited place falls to the ground plate. So this is the kind of energy it's given off. Now, how then do we find this? So what I'm going to do is, from here now, I'm going to say that change in this energy is equal to HF. I am looking for this F. So what I'm going to do now is to make F the subject formula. So let us start here. So I'm going to have 1.938 times 10 raised to power minus 18 is equal to H is the Planck's constant, which is given as 6.6 times 10 raised to power minus 34 times F. So this is F is equal to 1.938 times 10 raised to power minus 18 all divided by 6.6 times 10 raised to power minus 34. So F is going to be equal to, I will first divide these two. I'm going to divide the numbers first. Then before I deal with this one in terms of law of indices. So I have 1.938 divided by 6.6. I'm having 0.29 times 10 raised to power 34 minus 18. Remember, this is minus. It will go up and become plus. So this is 34 minus 18. So have F is equal to 2.9 times 10 raised to power 16, but it's going to be 15 now, hertz. So this is the frequency given off when there is a transition from a excited state to the ground state. Now the next thing they ask us to find is wavelength of the emitted photon. All right, so the wavelength of the emitted photon, I'm going to have this. Remember this, they said that C is equal to F lambda. I already know F and I already know C. C is given as 3.0 times 10 raised to power 8. So this is going to be 3 times 10 raised to power 8 is equal to F is there, which is 2.9 times 10 raised to power 15 times lambda. Therefore, I'm going to divide both sides. I'll have lambda is equal to 3 times 10 raised to power 8 divided by 2.9 times 10 raised to power 15, which is equal to, this is approximately 1. 3 divided by 2.9 is approximately 1, yes, which is going to be 1.0 times 10 raised to power 8 minus 15 is going to be minus 7 meters. So this is the wavelength of the emitted photon. All right, we are moving to the next question. It's an equation for photon emission. Calculate the wavelength of the radiated emission when an electron falls from an energy level of 0.4 eV to minus 13.6 EV, and 1 EV is this. All right. And there is one equation also I have to let you know. There is this equation that said that E is equal to EV. So the energy given off by a photon during transition is given as EV. So I can also say that this is this, all right? Therefore, we say that En minus E naught is equal to EV. Yes. Therefore, I'm going to express this in terms of EV. If E is EV, so I will have that, let E not be minus 13.6. So this is minus 13.6 EV minus 0. We have to find which one is, of course, this is going to be the lower, this is higher. So I'm starting with this one. So what I would say is 0.43 EV plus, remember minus is going to be plus 13.6 EV. Therefore, I now know that this is going to be 13 point, okay, this is going to be 14, because when you have 13.6 and 0.43, this is going to be 301, 41. So I'm going to have 14.03 EV. Remember that 1 EV is 1.6 times 10 raised to power minus 19. So what I'm removing this multiplied by 1.6 times 10 raised to power minus 19. So I'm having 14.03 times 1.6. So I'm going to be having 22.448 times 10 raised to power minus 19 joules, because it is energy. I can also convert this to a proper scientific notation, which is standard form, and which is going to give me the same answer. So this is this for the second equation. Then finally, an electron jump from an energy level of minus 1.6 EV to one of minus 10.4 EV in an atom. Calculate the energy and the frequency of the emitted electron. Okay, what we are going to do is to do this calculation, but then find the frequency. I'm still going to keep this as what we have, but then the lowest one is going to, this one is going to be 1.6 EV plus, remember minus is plus, 10.4 EV is equal to HF. Of course, remember we know what is our EV because we are looking for frequency. So this is going to be 10.6, 10.4, 1.6. This is 0, 2. 12 EV. Now, this is 12 EV is what we have. Remember, it's going to be 12 times 1.6 times 10 raised to the power minus 19. This is what we are going to have. 12 times 1.6, 19.2. So this is going to be 19.2 times 10 raised to the power minus 19 is equal to HF. And remember that your H is a Planck's constant. This is H for Planck's constant. And that H is given as 6.6 times 10 raised to the power minus 34, then multiply by this frequency. So I'm looking for the frequency of the radiation. So what I'm going to do is F is 19.2 times 10 raised to the power minus 19 divided by 6.6 times 10 raised to the power minus 34. So F is equal to 16.2, 19.2 divided by 6.6, which is 2.9 times 10 raised to the power, 2.9 times 10 raised to the power, 34 minus 19, and which is 15 hertz. So this is the frequency of this emitted electron from this energy level to the other energy level. Thank you, but remember before we go, we need to look into our Examguide app to pick out questions as regards to different exam bodies. Let's go. So coming in here, we have physics already. I will choose random. So we go to topics, and I will search for energy quantization. So I'm going to remove them and look for energy quantization. Energy quantization and duality of matter. So I'll be choosing this one now. Energy quantization. Okay, let's see a few questions from that. Okay, the first question we have here is, absorption line spectra exhibited by atom is as a result of transition of an electron from a higher to lower energy levels. Okay, instability of the nucleus, excitation of an electron in the atom, change in the kinetic energy of atom. So there are two options that are very good, and other options are not as good. So we have this one, transition of an electron from a higher to lower, excitation. Excitation is from lower to the upper one. So the option here is C. So when absorption occurs, it is electron in a particular energy level. When it is excited or heated or bombarded, as we learned in the lesson, we now move from one lower energy level to another one, and that is what we call excitation of an electron in the atom. Okay, we have this electron. An electron moves with a speed of this in a straight line. Calculate the wave length of the electron wave of mass this and Planck's constant. Okay, there is going to be a second lesson on this, so I don't want us to jump into this one that has mass. We have to check this. It said if a gas excited in a high voltage speed discharge and the light is examined in a spectrometer, dark lines are seen? No. Okay, this question comprises of energy levels according to Niels Bohr's atomic model. The energy level in the mercury atom is illustrated in the diagram above. Calculate the ionization energy of the atom. Okay, let's consider this, because in this case, we are not giving the value of EV, but we are going to leave our answer in EV because there was no value for that. Now, the ionization energy has to do with the energy level at infinity. So EI, E sub I, which is ionization energy, is given as E, this one, which is the infinity, minus E1. Maybe the next one, E naught. It can also be E naught because this one comprises of the ground state. So at this level, our E naught is given as minus 10.4 EV, and E at the infinity is given as 0.0 EV. So what we are going to do here is 0.0 EV plus, because minus is giving us plus 10.4 EV, which is the answer there for the ionization energy. EI is given as 10.4 EV. So the value of the EV was not given, but we are leaving ourselves our answer in that case, so which is going to be positive, and the option is C. Now, looking at this table, the table below illustrates the energy distribution for a various levels of an atom. Use it to answer questions. So we have energy levels for 1, 2, 3, 4, and we have the energy in terms of EV. Now they said we are given H 6.6 times 10 raised to the minus 34 joules seconds, and we have our electron 1.6 times 10 raised to the minus 6 coulomb, and we have our light as 3.0 times 10 raised to 8 meters per second. They say calculate the first excitation energy of the atom. The first excitation has to do from energy level 1 to energy level 2. That's the first excitation. So what we are going to do now is to use our energy equation. And that will be from change in E is going to be from E2 minus E1 is going to be HF. And then our F was not given. So let's find the change in the energy first. So E2 is given as minus 3.39, then plus 13.6. So we are going to have 13.6 minus 3.39. So our energy change is going to be 10.21 joules. So in that 10.21 joules, what we are going to do now is to find our, so calculate the first excitation energy. And remember that change in E is given as HF. So I'm going to find our frequency because frequency was not given. So to do that, I have 10.21 is equal to Planck's constant is 6.6 times 10 raised to the power minus 34 times the frequency. So the frequency in this case is going to be, F is going to be 10.21 all over 6.6 times 10 raised to the power minus 34. This is going to be times 10 raised to the power 0. So I'm having 10.21 divided by 6.6. So I will be having, this is 10.21. All right. The best option here is, remember, I have gotten my E, and this is going to be on EV. But 1 EV is given us. We have to find what 1 EV is. That would be our best option. And 1 EV is given us, 1 EV is equal to 1.6 times 10 raised to the power minus 19. That is what we are doing. So we're having 10.21 times 10 raised to the power times 1.6 times 10 raised to the power minus 19. So the energy there is given us 10.2 times 10.21 times 1.6. So I'm having 116.336 times 10 raised to the power minus 19. Yes, minus 19 joules. And then if you look at the options, we have this here. And then look at this one, 1.60. So if I convert this, if I move this point to this level, I'm having 1.6 times 10 raised to the power, and this is going to reduce by. So the option there is going to be option D. So I have this question here. It says, in a model of hydrogen atom, the energy level W sub n are given by the formula. W sub n is given as minus R all over n raised to the power 2, where n is the integer and R is a constant. Determine the energy released in the transition from N3 to N2. So they have given us a relation. So the relation they have given us is minus R all over n raised to the power 2. Now, where n is the integer, so what I'm going to consider is n I is 1, 2, 3. So for each of them, I'm going to use this particular value. So what I'm going to do, N3 is going to be this, minus R all over 3 raised to the power 2, which is minus R over 9. So N2 is going to be minus R all over 4, which is, 2 raised to the power 2 is equal to minus R over 4. So I'm going to say this minus this. So which is going to be 3 minus is going to be minus r over 9 plus r over 4. And remember, the LCM is going to be 36. 36 divided this is 4. 4 times this is going to be minus 4r plus 36 divided this is 9. 9 times this is 9r, which is going to be 9r minus 4r is going to be 5r all over 36. And the option we have there is B. And okay, this is also a question that is very similar to one I solved. Thank you for being part of this class, and you can also reach out to Examguide app to do more other practice. Bye.